Hi everybody, as a continuation of the previous class, here we are going to see the analytical study of Fermi systems at finite but low temperatures. Okay, finite but low temperatures, we are considering Fermi systems at low temperature. Here the value of Z, which is infinitely large at absolute zero. Z, we know it is exponential mu over kT. So when temperature is zero, mu will be, the Z will be infinity. Now for a finite temperature but low temperature, the Z will be very large in comparison with the unity. In this case, f nu of Z, where Z is very large in comparison with unity, in that case the functions f nu of Z is expressed in powers of log Z to the power minus 1. Okay, so it is or 1 by log Z. So for large values of Z, we can express the function, the Fermi Dirac function, in terms of the powers of log 1 by log Z, or log Z to the power minus 1. So f5 by 2 of Z is this, f3 by 2 of Z is this, f half of Z is this. Okay, and we have these two equations with us: P by KT, G 5 by 2 of Z over lambda cube, and N by V equal to G by lambda cube f3 by 2 Z, the two fundamental equations of the ideal Fermi gas. Okay, here for f5 by 2 Z and f3 by 2 Z, we are substituting these equations. Okay, now in the zeroth approximation, we are taking, we know this is f3 by 2 Z. The zeroth approximation of this series is, we take only the first term, and then in the first approximation we take these first two terms. Okay, so first we take the zeroth approximation. Okay, so zeroth approximation, our f3 by 2 Z will be 4 over 3 pi by 3 pi to the power half log Z to the power 3 by 2. Okay, this will be the zeroth approximation of f3 by 2 of Z. So that is substituted here. Okay, so we have this. So we find Z from this. Okay, or log Z from this. This is N by V. N by V is the particle density, that is equal to this. From that we find log Z, and log Z is this. Okay, so once we have found out log Z, we find mu is KT log Z. Okay, this comes from, we have used this equation at several places. Z is exponential mu over KT, so when we take log Z, we will get this. So mu is KT log Z. So we multiply this with KT to obtain mu. So that is h square by 2m, 3n by 4 pi GV to the power 2 by 3, which is exactly the Fermi energy. So in the last last lecture, we have calculated the Fermi energy. Okay, we had calculated the Fermi energy. This is the Fermi energy. Okay, when we considered the ideal Fermi gas at 0 Kelvin, absolute zero, the Fermi energy, the energy of the topmost filled energy level. So that we are getting here. So mu here, mu or the KT log Z is epsilon f here, which is identical to the ground state result. Okay. Now in the next approximation, okay, here, as I told, we took the zeroth approximation, only this term In the first approximation, we take these two terms for f3 by 2 offset. So that is taken here. So n by v will be this. Now again from this I am calculating what kt log set. Okay, kt log set is calculated from here. This is n by v. N by v is this, and here we have the log set, isn't it? So this log set to the power 3 by 2 is written in this form, and kt log set will be this, a mu kt log set, that will be, this is now our epsilon f 1 plus pi square by 8. Okay, now we are approximating this actually by, we are taking this minus 2 by 3 here. Here we have minus 2 by 3, that is taken here. So 1 minus pi square by 12, 2 minus 2 by 3 will be multiplied with this to approximate this. So 1 minus pi square by 12. Here I have written kt by epsilon f square. So why do I write kt by epsilon f here? That is taken from the 0th approximation. Here we know mu is kt log set, that is equal to epsilon f. Kt log set equal to epsilon f from the 0th approximation. So log set is what? Epsilon f by kt. Log set is epsilon f by kt. So that is substituted here. So we get this expression for mu for the first approximation of f3 by 2 offset. Okay. So once we have got that, let's find out u, that energy. U is 3 by 10 kt f5 by 2 set over f3 by 2 set. f5 by 2 set, this expression we know. This is a general expression. f5 by 2 set is what? It is this 8 by 15 pi to the power half log set to the power 5 by 2 and this series. Okay, f3 by 2 is this. So that is substituted here for u, that is given here for u, f5 by 2 set and f3 by 2 set. So u by n will be u by n. N I am taking to the left hand side, 3 by 2 kt, and then we cancel similar terms, and after processing we get 1 plus 5 pi square by 8 log set, and into this 1 minus, I am taking this series to the numerator. Okay, so we will have a power here minus 1, and that minus 1 as it combines with the series we will have 1 minus pi square by 8 log set to the power minus 2, like that. Okay, so this is basically positive here. Since this goes to the numerator, minus 1 will be here as it combines with the, so we are doing kind of sub approximations. Okay, then we are multiplying these two series and keep only the first two terms. Okay, we multiply the series and write the first two terms. The rest of the terms are there, we are not writing it. So as we multiply, the first term will be 1 into 1, 1. Then 1 into minus pi square by 8. So we will have minus pi square by 8 log set to the power minus 2. Right? Okay, then if we multiply 5 pi square by 8 log set to the power minus 2, we will have that term. Then 5 pi square by 8 log set to the power minus 2 into pi square by 8 log set to the power minus 2. Okay, so 1 plus, then combining the first two terms in the product, we get this, and rest of the terms are there. So this is 3 by 2 kt. This 2 gets cancelled. So we will have 3 by 5 kt log set 1 plus pi square by 2 log set to the power minus 2, like that. Then the kt log sets. Here we have the kt log set. That I am writing by the first approximation. By the first approximation, we have got KT log Z is equal to epsilon f into 1 minus pi square by 12 KT by epsilon f square. That is substituted here. Okay, so for KT log Z I am substituting what? Epsilon f into 1 minus pi square by 12 KT by epsilon f square. This series is not there. This is an error. Series, these terms are not there. Okay. And then what we do? We multiply this thing with this series. So the first term will be 1 minus. This is 1 3 by 5 epsilon f 1 plus pi square by 2 KT by epsilon f square, this thing, and this is written here. So we multiply. So first term will be 1, second term will be pi square by 2 KT by epsilon f square, third term will be minus pi square by 12 KT by epsilon f square, fourth term will be minus into minus pi square by 12 KT by epsilon f square into pi square by 2 KT by epsilon f square. So this is a kind of straightforward product, multiplying each term of this series by every term of this series. And the first two terms of that series will be this 1 plus 5 pi square by 12 KT by epsilon f square, 3 by 5 epsilon of this. Okay, so this is our U by N. So what is the pressure? So this we have calculated is U by N. The pressure of the gas is given by 2 by third of, or 2/3 of the energy density. So 2 by 3, 1 by V. For U I am writing this. U will be 3 by 5 N epsilon f. Okay, 3 by 5 N epsilon f. That will be U. Okay, that is written here. So this is what? N by V is written as small n, the particle density. Okay, so we get the expression for pressure. So pressure of the ideal Fermi gas, finite but low temperature. Finite but low temperature. Okay, it is this. And U by N is this. Okay. Then the CV. We are calculating the CV. CV is dou U by dou T. Okay, we have to differentiate this thing with the temperature. So that will be 3 by 5 epsilon f, and we are differentiating this with temperature. Okay, here we have KT square. So when you differentiate, you will have K square by 2T. Okay, so after cancelling the same terms in the numerator and denominator, we have this equation CV by NK. Okay, I am writing CV by NK, that is equal to pi square by 2 KT by epsilon f, like that. Okay, so what we observe is this is the equation for the specific heat, and this is the equation for the pressure. Okay, the pressure, and this is the equation for energy density for a finite but low temperature. Okay, and when temperature becomes 0, CV by NK becomes 0. Energy density becomes what? 3 by 5 epsilon f, that we have already got, and pressure becomes 2 by 5 small n epsilon f. Okay, at T equal to 0, we have already done this analytically. We have done all these things. So we get the same result. So CV by NK is pi square by 2 KT by epsilon f plus which is a series. And here we define a temperature called Fermi temperature. For our convenience, we define a temperature called Fermi temperature, which is epsilon f by K, Fermi energy by K. Okay. So here KT, for epsilon f I can write KTF. K get cancelled, so we will have pi square by 2 T by TF plus the remaining terms. So here we can write CV by NK as a series of T by Tf, powers of T by Tf. Okay. Now, how do we say a system is at a low temperature? The Fermi system is at a low temperature. It is when T is far less than this Fermi temperature. Okay. So the Fermi temperature is taken as a parameter, and if temperature of a given system, Fermi system, is less than Fermi temperature, we say the system is at a low temperature. Okay. So the Fermi temperature of the system, specific heat varies as the first power of the temperature. If you are taking the first term, approximating by the first term. Anyway, its magnitude is considerably smaller than the classical value. The classical value is 3 by 2. CV is 3 by 2 Nk, or CV by Nk is 3 by 2. So anyway, the overall variation of CV with temperature is shown in figure. For temperature less than Tf, okay, we are taking T by Tf on the x-axis and CV by Nk on the y-axis. For temperature less than Tf, that is T by Df less than 1. In this region, the CV by Nk is proportional to what? The temperature. CV by Nk is proportional to temperature if we are considering only the first term, because T by Tf, if T is much less than Tf, T by Tf itself will be very small. So these remaining terms will be very small, so that can be neglected. So CV by Nk is proportional to T. So it will be almost a straight line. Okay, so below the Fermi temperature, the CV by Nk will be almost a straight line, and then it varies like this. And for high temperatures, it reaches its limiting value 3 by 2, 1.5. The classical value 1.5. And we know whether it is ideal Bose gas or Fermi gas, at high temperatures it behaves like a classical ideal gas. Okay, the dotted line depicts the linear behavior at low temperature. Okay, the CV by Nk proportional to the temperature, the linear behavior is shown here. Now we calculate few more thermodynamic quantities at low temperature. One is the Helmholtz free energy. Helmholtz free energy is A equal to G minus PV, so that is mu n minus PV. G we know, mu n. So A by n is mu minus PV by n. So mu, I am writing mu by the first approximation. Mu is what? Mu is this. Mu equal to kT log z. That is epsilon of 1 minus pi square by 12 kT by epsilon of square. Okay, so that is written here. So that is written here for mu. PV by n. So where do I get PV from this? We know P equal to 2 by 3 U by V is given by this expression. Okay, so here PV by n, PV by n, that will be 2 by 5 epsilon of 1 plus 5 pi square by 12 kT by epsilon f square, like that. This also can be written as T by Tf square, okay, in terms of Fermi temperature. So here we are writing it like this. So this is our PV by n, and we subtract this term from this, and we get this expression. And finally A by 5 is 3 by 5 epsilon f 1 minus 5 pi square by 12 kT by epsilon f square, kT by epsilon f whole square, like that. So this is our Helmholtz free energy per particle. Now we find the entropy. Entropy is U minus A by T, and S by N is U by NT minus A by NT. Again we substitute for U, and A by NT, that we got A by N is this. U by N we already know. U by N is this. Okay, U by N is this. And A by N we substitute Okay, we substitute here a by nt like that, and we finally arrive at this relation s by nk equal to, okay, s by nk, I'm writing s by nk by taking k to the side. That is k pi square by 12 kt by epsilon f. Okay, kt by epsilon f plus the remaining terms. So this is the expression for entropy. And again here we see this equation obeys the third law of thermodynamics. What third law of thermodynamics is, as temperature goes to zero, approaches zero, entropy also approaches zero, which is the third law of thermodynamics. This equation perfectly satisfies third law of thermodynamics. Okay, so few thermodynamic quantities are also determined. Remember this thing we have done for a degenerate case. Okay, degenerate case, finite but low temperature.